Okay, so for the next pedagogical talk, we have Professor Nikku Madhusudhan from Institute of Astronomy and University of Cambridge. So definitely he does not need any introduction. Okay, and I'm aware that all of you have been waiting eagerly to hear him talk about observations as well as K218b, isn't it? So over to you, Madhu.
Thanks, Jayesh. Thanks to the organizers for inviting me to join all of you guys in this exciting meeting. So no pressure for me, given all your expectations, and I hope to live up to your expectations in the remaining 3.5 hours of this afternoon. So we'll cover a broad range of topics. I was asked to talk about observations, but I was also told that there are expectations beyond just observations. You want to learn a little bit more about all the everything that's happening on K218b and habitability, biosignatures, and so on. So we'll try to cover as much ground as possible during this afternoon. So, and I was also told this is a pedagogical lecture, so I'll try to use the slides, but also some Blackboard just to give you a sense of some basic concepts and so on. So at the end of these few hours, our goal is for you to understand exactly what you're looking at when we are talking about an exoplanetary atmosphere, which part of the planet are we talking about, what kind of process are we talking about, what kind of observations are possible, what is not possible, and what is the absolute cutting edge in this area that's happening. So that's my broad remit, but obviously we'll take lots of questions. Any questions you have, you can ask me. Right? Cool. So that's just the admin details. But before I start talking about the lecture, I want to pause and take like a long view of this whole subject. I mean, we are having a seminar here like any other scientific topic, and we'll go through the motions, we'll go through talking about the subject, the background, the latest and greatest. But if you just think about it, what is this subject, right? Just take a long view as the big picture. We are sitting here on a planet and asking what is the atmospheric composition on another planet that could be hundreds of light years away, right? And you'll see that in most cases, we are not even seeing that planet. We are indirectly inferring the presence of that planet. And we as humans have become so ambitious. We are ambitious by nature, but this is the characteristic of our ambition, that we are not even seeing the planet, but we want to find out what's in the atmosphere of that planet at a few percent level abundances, like chemical abundances. And eventually we want to use those abundances to say if there is life on that planet, right? So this is, if you will, irrespective of the pedagogical and the scientific nature of the talk, this is very human, an endeavor to be able to sit on one part of the planet or on a planet, as we are talking about Earth here, and just look at the cosmos and say, what else can I understand about a planet that's trillions of miles away, and can I relate it to my own existence here on Earth? Right? So if you just think about it as a human, it brings that subject that much closer to home. And the rest of this whole session, I'm going to tell you about how to relate what we are seeing there to your daily experience. So you are sitting in an atmosphere right now, right? So we're talking about atmospheres of planets elsewhere, but you're sitting on a planet and breathing the air, and you are witnessing that atmosphere. So all the things that you can relate to here, the composition of this atmosphere in this room right now is essential to your and my staying alive. Right? And that's exactly the composition that we are trying to measure elsewhere. The temperature in this room, the pressure, all of these things are basic essential quantities. You go outside, you see clouds, you see the wind, all sorts of things. There is a star that's irradiating the planet. All of these things, which are our daily experience, are things that we are trying to characterize on planets that are trillions of miles away. Okay? So we are going to go through how we'll make those observations and what we can measure in terms of those quantities. So I hope you get that experience, that immersive experience throughout this session, and you're free to stop me anytime during this lecture and ask me questions if I'm losing track. Okay, so are we ready? Sorry if that was too philosophically heavy. Excuse me, but I feel like so I've been working in this area for about 20 years now, and I still can't come to grips with the fact that we are where we are today. You know, I was in 2008, 2009, I was a PhD student, and JWST was supposed to be around the corner. It didn't come. It would be another more than a decade when it came. And I just can't believe that here we are talking about, you know, these big instruments and getting these kinds of observations and getting the kind of detail we're getting. So it's very surreal. So let me walk you through that frontier. So this is going to be the outline. So I'll give you a brief background. I know you have covered a lot about exoplanet detections and a little bit about atmospheres and so on. But I'll revise some of those topics to refresh your memory. And then I'll talk about atmospheric observations. I'll also talk about, once you observe, make an atmospheric observation, how do you extract the atmospheric information, the chemistry, the temperature structure, and so on. That's atmospheric retrieval. And then I'll talk about this recent developments, which is what many of you wanted to hear about habitability, biosignatures, the K218b developments and debates around it, what new observations are coming. And then I'll stop with future outlook. Okay, going back to my philosophical view, this was just 30 years ago, right? Our notion of what planets are like elsewhere was just this. So we didn't have 51 PEG in the early 90s, but we had the solar system planets, and that's it. So all the theories of solar system bodies, or of how planets should be forming, came just from our own experience of the solar system architecture. Now, what is that architecture? If you pay attention, you know that the giant planets, the ice and gas giant planets, sit in the outer parts of the solar system, and the rocky planets, Earth and smaller planets, sit in the inner parts of the solar system, right? So based on that architecture alone, you can devise a whole formation, a whole theory of planet formation, which is basically what we did for a century before exoplanets came along. Okay? So all our mechanisms for planet formation, what planetary interiors will be like, all those hypotheses were based on the solar system. And the first planet that showed up was 51 PEG B, which had no analog in the solar system. So this is a planet that is sitting about 1/10 of the distance Mercury is to the sun. The innermost planet is to the sun, and had no analog in the solar system. So for a while, for several years, people were arguing whether that was an actual planet. Okay? But then, fast forward today, so we have a zoo of planets out there. This is not even the most up-to-date, recent enough, but today we know of over 6,000 exoplanets, and they populate the entire regime in planetary masses and radii and so on, and detected with various techniques. And you have heard of all these techniques in the last few days. So if you look at the demographics of exoplanets, you know by now that exoplanets are extremely common. The statistics are like almost every star out there should have a planet of some kind around it. Now that is going from knowing no planet at all 30 years ago. So when people talk about exponential progress in exoplanetary science, this is what they're talking about. In just over 3 decades, within lifetimes for many of us, we went from not knowing any planet outside the solar system to today saying that almost every star should have a planet of some kind around it. That is crazy if you think about it, right? Just the big picture of it. Most abundant of this population, the exoplanet population, are planets in this regime. So you see, these are just sizes, planet sizes. And in the solar system, you have the Earth and smaller planets that are smaller than Earth. And then the next size range is the ice giants, Neptune and Uranus. That's about 4 times Earth size. Okay. And then the next size range is Saturn and Jupiter, the gas giants that are around 8 to 10, Jupiter is around 11 Earth radii. So, and there's nothing in between. So there's a certain quantization in sizes if you just look at the solar system. But when it comes to exoplanets, there is no quantization. right? It's a continuous distribution of sizes. So just by detection alone, you know that there's a vast diversity of planets out there that surpasses by great amount what we see, the diversity we see in the solar system. So even without going any further into atmospheres and so on, you know just from the sizes that there's a lot of physics and chemistry that's going on that we have no analogs for in the solar system. We don't see such planets. Most importantly, the planets in between these two, Earth and Neptune in size, these are known as the sub-Neptunes, smaller than Neptunes, dominate the exoplanet population. So we will revisit this population towards the end of this session. So when we talk about habitability and so on, we'll come back to it. But I just want you to know that just by detection alone, we know that there's a vast diversity of planets out there, which means going in, we are already expecting that there's a vast diversity of processes, chemical processes, physical processes, atmospheric processes, interior processes, formation processes. You expect a lot of diversity in all of those things. So the entire effort in exoplanetary science over the last couple of decades has been to characterize that diversity across all those areas. So someone interested in planet formation is looking at how these planets are formed, but there are people who are looking at interiors and see, what can be the vast diversity of these interiors, what could be the state of materials in the interiors and so on. We are not going to cover all those aspects in this talk, just so we are clear. We are not going to talk too much about planet formation or about interiors. We'll touch a little bit about interiors, but not a whole lot. But atmospheres we will look at. So we know that exoplanets are extremely common and small planets are extremely common as well. Okay, so that's where the distribution peaks. And there are several facilities, space-based instruments that have contributed to these various detections. So you've heard about the Kepler mission, which has discovered thousands of planets. TESS is currently operational, also detected lots of planets, especially around bright stars. Cheops is another European mission. Plato is going towards the end of this year or early next year, also to look for habitable zone planets around sun-like stars. So lots of these missions have contributed to these detections. So now that we know there are planets, lots of planets out there, thousands of planets out there, why do we need to look any further? Anyone wants to take a wild guess? Why do we want to find more planets if we already know 6,000 of them? Sorry? So Earth twin is a motivation. Is there any other motivation? So finding an exact Earth analog, the point made was that in all of this, we still don't have an exact Earth-like planet around a sun-like star. So that's one motivation, to keep looking for longer period planets. So that's a formation angle, but purely from the detection, why do we need more planets? So we want to look at more diverse, to see if there is any further diversity than what we already know. Please. Sure. Yeah. So that all of these are very good points. So you can always populate this diagram more and more to overcome detection biases that we may have, to find literally Earth twins and so on and so forth. But the most important reason for designing all these missions is not, there are some missions that are designed for Earth twins. Plato is going to do that. But the most important reason is that many of the planets we know so far, most of the planets are around faint stars. So if you want to understand these planets further, now you know the planet is there, you want to know more, right? You want to know what its atmosphere is like, and what, the composition, the physical process, then you want to be able to characterize them. And the only way you can do that is if the systems are closer in. That's how you get a higher signal to noise. Okay. So a lot of these missions are focused on finding planets around nearby stars. The new observational efforts are to find planets around nearby bright stars, so we can then characterize their atmospheres. So you have seen all these detection methods, but just to refresh your memory, I'll play the movie for the transit method. We have covered transits here, right? Yeah. So we have covered that. So transits, then as the when the planet is not going in front of the star, you'll see just the starlight. But when the planet comes in front of the star, then you'll see a dip in the starlight. Right? Very simple. As a technique, it's very simple. And you'll see that when the planet goes behind the star, you'll see another dip as well. So that's known as the secondary eclipse. This is because when the planet is just here, you see the day side of the planet. And when it disappears, you get back the starlight, so you'll see a little dip. Okay? So both these configurations are important. This obviously gives you just the transit depth, so you get the size of the planet. But I'll come back to both these configurations when we talk about atmospheres. So this is one method, the transit method, to detect planets. So these two dips that you just saw, the transit depth is proportional to the radius ratio squared, just the area of the planet disk or the stellar disk. The occultation or the secondary eclipse I mentioned, that is the small dip, is proportional to that same quantity, but weighted by the brightness of the planet over the star, okay? Because you're seeing the radiation from the planet just before eclipse. So just so you know. The other technique, obviously, is the radial velocity method, which you also saw. And let me, again, refresh your memory on how this works. So you're looking at the star-planet system, and you're especially monitoring this star at high resolution. You're seeing a spectrum of the star. So as the star goes around the center of mass of the system, the spectral lines, high resolution spectral lines of the star are Doppler shifted. Okay, so you see the blue shift when the star is coming in towards you, red shift when the star is going away from you, and from those shifts, you can calculate what the radial velocity of your star is. And from the radial velocity of the star, from the semi-amplitude, you could put a constraint on the planet mass, the minimum mass of the planet. So we have gone through this earlier in this workshop. And finally, the third approach is direct imaging, which you probably also saw, where this is the simplest conceptually, which is you just take a picture of the system. Okay. The minor problem, of course, is that the planet is a lot fainter than the star. So you need an efficient way of nulling out the star. So the central region you null out, that's when your planet pops up. So you need to make sure that your instrument is nulling out this star well enough that the planet-star contrast is achievable, that you can actually see. These contrasts are very small. They are of the less than a few tenths of parts per million, so less than 10 to the minus 5, maximum 10 to the minus 4 for a giant hot planet. But they're very small, so which means you need very efficient techniques. So this is the most obvious way you would think you would detect a planet, and people had been thinking about it from the 1990s. But this was the last method that had detected a planet because it is so hard to do that nulling. Okay. So this is direct imaging, and yeah, in late 2000s, several planets were detected. I'll just put these 2 points here for completeness, which is the 2 challenges with direct imaging. One is the low planet-star flux contrast, and also that the closer the planet is to the star, the more difficult it is to remove the star. So if you just said, let me take the solar system and can I find it in direct imaging, that is very, very hard because both especially for Earth-like planets, is almost impossible right now. Okay, because the planet-star contrast is low and the planet is also very close to the star. So the solution people came up with, and that's how the first detections were made, is if you have young planets at large orbital separations. Large orbital separations, because that beats this problem. You're well separated, then the residual flux from the star is not contaminating your planet spectrum. And young, do you know why young planets are better to observe in direct imaging? Anyone? Sorry? Luminous, right? So when planets form, they form hot and large and then contract over time, radiate away that energy and cool, right? So present day Jupiter is obviously 1 Jupiter radius, but if you look at Jupiter when it was a few tens of millions of years old, it could be up to twice the size. And the temperature today is order 100 Kelvin. It could be easily 1000 Kelvin very early on. So that combination, large size and large temperature, means your luminosity is higher, means your planet-star flux contrast is better, right? So that is why you see these directly imaged planets most of the time. You see that they're young giant planets. So that is basically all I want to say in terms of the detection techniques for completeness. And my motivation in bringing all those techniques is because these same tools will also be used for atmospheric observations, right? So which are the planets that are most conducive for atmospheric observations? So most of the time, it's either transiting planets or directly imaged planets, but I'll also show you a technique where the planets don't need to transit. You can still detect their atmospheres. That is also with high resolution Doppler spectroscopy. Okay, so now armed with these basic tools for detecting planets, let's look at how we observe their atmospheres. Okay, so the big picture in all of this, so this is how I started this lecture, right? So you're sitting on a planet and you have an atmosphere above the planet's surface, right, around you. You should be able to relate to all these processes based on Earth experience. Okay? So close to the surface, so on Earth, this doesn't apply because our surface is at 1 bar. But if you take a planet like Jupiter, for example, a planet with a thick atmosphere, so you can go to very deep, high pressures and deep into the atmosphere. And there comes a point where the pressures and temperatures are high enough that the reactions happen very fast. The chemical reactions happen very fast and chemical equilibrium is satisfied. Okay? So that's the deep atmosphere. I'm basically giving you a 101 lecture on all of atmospheric chemistry in 5 minutes, in like maybe less than 5 minutes. So deep in the atmosphere, chemical processes tend to be in equilibrium just because of the high temperatures and pressures. But as you go higher up in the atmosphere, you have other processes that compete with your reaction time scales. Okay? So for example, atmospheric circulation dynamics can move stuff around faster than reactions can achieve equilibrium. So naturally, that means your atmosphere can be driven out of equilibrium. So it could be atmospheric circulation, which is lateral mixing, but you can also have eddy diffusion vertically. So you can have vertical mixing also in these atmospheres. You have clouds or hazes in the atmosphere that you're familiar with. Those can condense out species. Hazes can be from photochemical mechanisms as well. So those could be non-equilibrium products that also modulate your experience in the atmosphere, be it your temperature structures or various other processes, rain, and so on. You also have thermal inversions. Are people familiar with thermal inversion? Like is there an example of a thermal inversion on Earth? Yeah? Sorry. Yeah, so the stratosphere, right? So the Earth's stratosphere, beyond a certain around like 20, 30 Kelvin, the temperature starts increasing as you go up. That won't be closer to ground if you're going higher up. It gets cooler and cooler, but there comes a point where the temperature starts increasing. And why is that? Not on Earth. Ozone, right? Yeah. Yeah, so for hot planets, you can have metal oxides doing that, the absorption. But on Earth, it's the ozone layer, right? What is the ozone layer doing? It's absorbing the incoming UV light, right? So in one sense, it's protecting the surface from the UV light. And that energy is being released in the upper atmosphere, by upper, I mean in the stratosphere, and causing this sort of increase in temperature. That phenomena is a common phenomenon. You can have other molecules that are strong UV absorbers and can also cause thermal inversions. Point is, this simple fact here, this is a cartoon of a temperature profile with no inversions. This is one with inversion. All that is saying is that your chemistry is coupled with your radiation field, and the radiation field and chemistry both modulate your temperature structure in the atmosphere. Right? So all these processes are talking to each other in a real atmosphere. Of course, when we study these things, theoretically, you isolate these processes and study one at a time. That's the scientific method. When you observe it, you also try to pick out one aspect at a time. But you also want to realize that in a real atmosphere, all these processes are happening at once. So when you're thinking about exoplanet remote sensing, you have to think about the challenges, which is, first of all, you're not seeing the planet. You're only seeing a spectrum. You're trying to infer some of these properties from the spectrum. And then you're trying to tease out these various processes from those inferences. So it's always good to have this context in the back of your mind for robustness. So that's all is still the lower atmosphere. And by the time you get to the stratosphere, about a millibar or so, you can hit thermal inversions and so on. And then you keep going. So far we have seen that the chemical equilibrium at the bottom of the atmosphere can be disturbed by various processes, circulation, mixing, and so on. And then if you keep going, at some point, photochemistry takes over, right? Because the photochemical timescales, what does photochemistry do? It can dissociate species, right? So you can have a molecule and the molecule can be dissociated photochemically just by photons. But you can also have photochemical byproducts, create new molecules that are a result of dissociation of some other molecules and reactions with some other radicals and so on. So photochemistry takes over the composition as you keep going. And eventually, if you keep going up in the atmosphere, every single molecule will be dissociated at some point. Why? Because you have a spectrum of the star, right? That goes all the way from XUV to infrared. And the XUV will be absorbed very high up in the atmosphere. Where is that going? All those photons are going into destroying the molecules that are formed. Okay? So that's where the exosphere is. So that's where atmospheric escape happens. So all these molecules will be dissociated and those atoms eventually escape to space. Okay? So that's the big picture of an entire atmosphere for you. Theoretically. Now, what are we trying to do observationally? We are trying to use different probes. No one specific wavelength or frequency will be seeing all these processes, right? Why? Because as I just said, photons see different chemical species at different parts of the atmosphere, right? So your atmosphere is split into various compounds or atomic species over this height, and different wavelengths, different radiation of different frequencies are being absorbed at different levels in the atmosphere. So if you turn that story around, you can say that I can use different frequencies of light to probe different parts of the atmosphere. And that's remote sensing for you, right? Depending on what wavelength you pick or frequency you pick, you probe a different part of the atmosphere, and from that you're detecting certain chemicals, and from those you're working out the processes related to that part of the atmosphere. Okay? So for example, as I already mentioned, if I'm looking in the UV, I'll be probing the very upper part of the atmosphere, looking at these atomic species escaping or present in the exosphere, in the upper part of the atmosphere. So atoms, ions, and so on. If you start going to optical, you can probe slightly deeper, and that's where you probe all these various species which have strong optical absorption, like TIOVO you mentioned, which is in hot Jupiters, in giant planets, very hot, highly irradiated planets. Those are molecules that can cause thermal inversions. But then in cooler planets, they may not be abundant, but sodium and potassium, atomic sodium and potassium can still be good optical absorbers. Okay? All of those things you can probe in optical. But by the time you get to infrared, the infrared radiation sees all the way to the deep atmosphere. Okay? Why? Because the infrared radiation is probing molecules. And you know from our 5-minute chemistry lecture that molecules are in this part of the atmosphere, because if you go higher up, they're dissociated. Right? So all that molecular absorption is being seen here until you get to a certain point in the atmosphere, maybe a bar or so, where the atmosphere becomes optically thick to all radiation. Okay? So at that point, you're no longer probing. So you may ask, so how deep can I probe in an atmosphere? It is typically around a bar. That's a good, a bar is 1 atmosphere, 1 Earth atmosphere, roughly. That is the depth to which you typically is your optical depth at the longest wavelengths. So here, you probe all these various molecules. And the beauty of this is that because you're probing these molecules, you're also probing all the processes that are modulating those molecules. Okay? So this is where, if you hear things like, oh, we detect photochemistry, or we detect vertical mixing in an atmosphere, That is because that inference is coming from the fact that we use some infrared wavelength range to detect a specific molecule that is a tracer of a specific disequilibrium process. So by detecting that molecule and measuring its abundance, we can work out what the underlying process is. Okay? So molecules as probes of atmospheric processes, that's what we are trying to do in all of this. So that's the big picture of atmospheric remote sensing. Any questions? Cool. Yeah. So this is just a graphical, a cartoon of describing things. But yeah, clouds hazes especially, can have an almost uniform continuous distribution in the atmosphere. They're not specifically tied to a specific layer. And the altitude depends on the strength of your vertical mixing also, right? Because those two are also coupled. I'll give you an example. So some cloud forming species may not be abundant in the upper atmosphere, but you have to loft them from the deeper atmosphere to upper atmosphere and then form condensates on top of them. Right? Cloud forming nuclei, for example, may not be abundant in the upper atmosphere, but may be abundant in the lower atmosphere. By mixing, you raise them up, and then your temperature is lower in the upper atmosphere, and then you can form condensates on top of those nuclei. So all of these processes are talking to each other.
That is not what we do. That we do negligible in case of.
Yeah, I mean, this is a generic schematic for any planet. All this is to say is that you'll have a continuous distribution of all these processes through the atmosphere. And broadly speaking, in the deep atmosphere, you'll have chemical equilibrium. But most disequilibrium processes, other than photochemistry, happen between about a bar and, let's say, about a millibar before photochemistry takes over. That is all the point we're trying to make here. Does that make sense?
Yeah. Okay. Like generally, we can ignore those very specific things that might happen at the north.
Oh yeah. Okay, yeah. So from an exoplanet science point of view, because we are seeing a dot, we are not even seeing the dot, right? So most of our inferences are coming on planet-wide averages. So we can only make like average inferences, not spatially resolved inferences yet. So specific locations we are not sensitive to just yet. Yeah. So very good question. So most of the time, chemical equilibrium is not strictly justified, but there are regimes in parameter space where chemical equilibrium is a very good assumption. For example, if you go to a hot Jupiter above, let's say 1500, 2000 Kelvin, vertical mixing will change your composition. Think about this, right? Vertical mixing will change your composition only when the composition of your lower atmosphere is significantly different from the upper atmosphere. But there is a temperature range. If you go beyond, let's say 1500 Kelvin, your composition is pretty uniform across the board because it's all hot. And at that point, vertical mixing is not changing your composition very much. So then equilibrium chemistry is a decent assumption. But if you go to a warm or cold object, and we will come to that later in the afternoon, where you will have planets with surfaces, and then the surface can interfere with your equilibrium cycling, and so on and so forth. So those are planets where you cannot assume equilibrium. So it depends on the problem at hand. Okay? Cool. So, yeah, please. Earth is not a very good planet for equilibrium. It's almost entirely in disequilibrium. The atmosphere, most importantly, because there is life, we are driving it out of equilibrium. But Jupiter is a good example. So Jupiter, for example, if you look at a spectrum of Jupiter, you'll see a lot of methane. And methane, you expect in chemical equilibrium in a hydrogen-rich atmosphere, you expect a lot of methane. And that we see in Jupiter, Saturn, all solar system giant planets, you see a lot of methane. It's in chemical equilibrium. The concept of equilibrium is basically you take a box of gas, keep it at a certain pressure and temperature, and let it relax in steady state. What is the composition? What is the molecular composition you expect those atoms to be in? So if I put that box at a temperature of about, let's say, 300 Kelvin, and I have a solar composition gas, which is hydrogen dominated and so on, at 300 Kelvin and 1 bar pressure, I expect most of my carbon atoms to go into methane. I expect most of my oxygen atoms to go into water. That is what I mean by chemical equilibrium. Sorry? Yeah, I mean steady state. If you leave the box by itself without any shaking or anything, at some point it will reach, by definition, it will reach that state of equilibrium, right? Where the composition is not changing anymore. Right? If you want a more technical definition of that, it's where your Gibbs free energy of the whole system is minimized, basically. And it's a very simple calculation you can do and show that methane will be the dominant product. Because there is a methane CO reaction, which is the main carbon reaction, which is highly temperature sensitive. So below a certain temperature at 1 bar, it's about 1100 or so. Below that temperature, you expect most of the carbon to be in methane. And you see that in solar system planets. Sorry? Yeah. Yeah. Yeah, every system without an external perturbation will tend to minimize the Gibbs free energy. And for a hydrogen-rich atmosphere, you'll end up with methane, with most of the carbon. It's as simple as that. So you see that in solar system planets, but on Earth you don't, because the presence of a surface already cuts off your equilibrium. You need high pressures and temperatures for equilibrium to hold. But on Earth, you don't get to high enough pressures for that to hold. And then you're constantly changing the atmosphere with a lot of these other processes. Okay?
So you said that in the infrared, everything goes to high optical depth at 1 bar. What's the emission or absorption mechanism?
Yeah, so we are talking about giant planets here. Of course, if you have a surface, then that cuts it. But if you have a deep atmosphere, for let's say hydrogen-rich atmospheres, the H2H2 collision-induced opacity gives you the continuum.
So it's a dense forest of lines.
It's a continuum opacity.
So it's a continuum.
Yeah, so, and that is pressure dependent, right? So already by 0.1 bar, you start to see the photosphere in some wavelengths. By 1 bar, it's almost entirely opaque. Okay. So that's that. So I've given you like the broad brush of all the things that you can see. I will say at this point that almost every single process that's listed on here has been observed in an exoplanet already 10 years ago. So this is old news. I'm giving this as a pedagogical lecture, so we're going through like the basics, but every single one of these had been already found 10 years ago. That's how fast this subject moves of exoplanetary atmospheres, right? So let me give you some basic design considerations for what is going on here. So you have an atmosphere around a planet. Sorry, I'll do some quick estimates on the board here. So the math is actually quite simple, I mean, to get a broad understanding. So you have this planet and you have an atmosphere around it, right? So your transit depth is just RP or R star squared, right? So this everyone knows, right? How you got this is trivial. What we want now, when you're doing transit spectroscopy, we are trying to look at the atmosphere, right? So what is my signal due to the atmosphere? Anyone? So now I'm asking, by the way, these are all trivial questions. There is no complex math here. So feel free to take a wild guess and you'll most likely be right. So that's my atmosphere, right? So what is the contribution to the transit depth from just this atmosphere? If I say my atmosphere is of height h. Trivial, right? Anyone? Right, so it'll just be this. Right? So all I'm doing there is that so now if I have an atmosphere as a function of, whose opacity is a function of lambda, so I just have some Rp prime over R star squared, and this Rp prime is just Rp plus H, which is the atmospheric height over R star squared, right? So then I'll get this term, let me call this delta naught, right? So I have my delta naught plus 2 Rp H over R star squared, plus higher order term, which I can ignore, which is small, right? It's square term. So what I'm talking about when I say amplitude of a spectral feature is if I have my lambda here and I plot my delta lambda, what I'm seeing is some spectral feature like this from some molecule, right? So the baseline of this, which is the high optical depth regime we talked about, that is what is your delta naught. Right? So that is your bulk radius of the planet where it is entirely opaque at all wavelengths. So that's your delta naught, which is just your some Rp naught squared over R star squared. But then your actual atmospheric feature is this. And that is coming from this term here. Right? So now what the entirety of atmospheric studies, remote sensing that we are doing is in trying to estimate that H, and all your physics and chemistry that you infer is all in that H. Basically, that's what it all boils down to. Now that H is you can approximate is some number of scale heights of the atmosphere. People heard of scale height, right? So what is it? Just that, right? So this is just from hydrostatic equilibrium, your pressure decreasing exponentially. So you can already see, if you just looked at this, you can already, and those are the equations there, you can already say, what are the kinds of planets that will maximize my signal? What is your signal? My signal is the spectral height. This is purely for transmission spectrum I'm talking about. Emission spectrum, I'll come to that in a second, but let's focus on transmission spectrum. Then what are the properties of a planet that will maximize your signal? Anyone? Right? So you want as large an Rp, as small, sorry? Yeah, exactly. So you have higher Rp, smaller Rs, and then when you go to H, you have higher temperature, lower mu. That's basically it. G doesn't, G also in principle, right? Lower G should also help. G is comparable because it's an M over R square term. The dynamic range for that is only a factor of 3 between Earth and Jupiter. So it's not that much. But mu varies a lot, right? For Earth, what is the mu for Earth? What is the composition of the Earth's atmosphere? Order 30, right? It has to be 30, right? Right. But if you have Jupiter with a hydrogen-rich atmosphere, what is it? 2, right? Order 2. So you have a factor of 15 difference in the scale height. G is not that much, it's a factor of 3. T is not that much, it's also a factor of 2 or 3 between Earth and Jupiter. But it's the mu that gives you an order of magnitude larger scale height. In retrospect, this is trivial, right? You can imagine that, like by intuition, but this is where those numbers are coming from, right? So larger planets, lower mean molecular weight, hotter planets are the ones that are best suited for transit spectroscopy. And that is why the first observations were made for hot Jupiters, because those are the easiest targets. It's also the same reason why they were also the first planets to be discovered by all these techniques, by transit and RV, because larger planets means larger transit signal. This delta naught is larger as well. Okay, so these are some basic design considerations.
Here we are considering the equilibrium temperature.
Yeah, I mean, when you have not made an observation, you need some average T estimate.
Or suppose there is some planet which is hot because of some process happening in the atmosphere, then also it can.
Yeah, we don't know that. When you're making an observation, you take the information that you have and make a prediction for a
That
signal.
case, if we observe something, then we can predict T with that, right? And if that is different than the equilibrium temperature we estimated,
Yeah.
we can estimate the temperature.
You can put a constraint on the disequilibrium in a radiative disequilibrium, which we will come to towards the end of this lecture. Okay, in about like 20 minutes, we'll come to that. Okay, so now you get the broad brush idea, right? So I've summarized it all there. So in order to get large signal, you need large and hot planets, small and cool stars. If you have sun-like stars, then hot Jupiters are your best bet, because the smaller planets you go, the harder it gets, right? We've only talked about transit so far, but the same applies for this thermal emission also, this eclipse depth I was talking about earlier, right? Because that is just this transit depth modulated by the brightness, in this case thermal emission, just the Planck function of the planet over that of the star. And that goes as, that is temperature dependent monotonically, so higher temperature means higher brightness. So that also satisfies this, which is the larger and hotter planets are better in emission spectrum as well. So now when it comes to star, we talked about small stars are good, but another important factor, which is what I mentioned when we were talking about new missions. Why do we want new missions? And I said we want to find smaller, closer and closer stars. That's because of this, is that bright star means you have higher signal to noise, because the signal, this is only one part of the story. Your theoretical signal is only one part of the story. But in practice, when you're observing, you measure this with error bars, right? Now, where do you get this error bar? From the star, right? So this depends on how many photons you're collecting from the star, because the transit duration is fixed. So the more photons you can collect within a certain amount of time, the smaller your error bar will be. This is why bright stars are very important. But also you have to be careful. If the star is too bright, we don't usually have this problem, but sometimes your star can be too bright and saturate the detector. And that won't be good either. There are only like a handful of stars that do that for our best telescopes, but that's also sometimes a problem. And the next bit you have to be careful about is that your star can be active. If it's an active star, then that can corrupt your observations as well. So you want a relatively quiet star, bright star, and then so on, and then you'll get great observations. Now you can have a great planet and a great star, but you also need the optimal spectral bands where you want to do the physics you want to do, right? If you want to, let's say, detect methane or carbon monoxide or carbon dioxide, you want your observational capability, your instrument to have, you want a spectrograph in that wavelength region. It's kind of obvious, but I want to make that clear, is that it's not a given that you could do any kind of physics with any kind of spectrograph. You have to choose your spectrograph carefully. Okay? And we now have such facilities. So this is a summary of what you learned from different wavelengths. I already mentioned it. In the UV, you get all these ionized metals and Lyman alpha and so on. And that gives you a constraint on the atmospheric mass loss in these exospheres. You can also look at visible. You can constrain all these things. Infrared, you can constrain all these things, as I already mentioned in the cartoon earlier. So now let's get into some actual observations. Are you ready? Armed with our basic background. So I'll take you through a historical tour of early observations. Observations happened even before these dates, but these were first times we were getting robust molecular detections, which is where much of the impact has been generated in the last decade or so. So we saw these examples. So primary eclipse, secondary eclipse. And this is this is the first robust water vapor detection with what is known as the HST wide field camera 3 in this wavelength range. So you can see that is similar to what I drew on the blackboard just now, right? So small error bars. Now take a guess, or you can read off from the plot what these error bars are like. How big is this error bar? Take a guess. These error bars are a few tenths of parts per million. And you can read off what the baseline is, what the delta naught is. It's about 1%, right? 1.5% or so. What is that telling you? So here, where is my chalk? So this is one, if this is 1%, my RP over R star is a factor of 10, right? It is 110, right? I'll give you like a quick back of the envelope. Do you know how big Jupiter is compared to the sun? Right, a factor of 10, right? So R star is about, our sun is about 10 Jupiter radii, and 1 Jupiter is about 11 Earth radii. It's interesting, isn't it? They're all separated by a factor of 10. Okay? So you already see from this 1% that it's got to be a Jupiter-sized planet, if you know that your star is sun-like. So that was the first hot Jupiter detected in transit, HD 209. So that is telling you that it's a Jupiter-sized planet, but this amplitude is only a few tenths, this amplitude is a few hundred parts per million. And that tells you, if you do the scale height calculation and so on for the equilibrium temperature, it's about a few scale heights, 2 or so scale heights, 2 to 3 scale heights. So it is smaller than you would expect. Normally, for a full feature, you would expect anywhere between 5 to 8 scale heights. This is a bit smaller than that, but we were able to detect it because of the small error bars. These are some early observations of another planet, another ultra hot Jupiter. This is around 2700 Kelvin or so equilibrium temperature in various facilities. These were all obtained with the Spitzer Space Telescope, which is now long gone in the infrared, and these points are obtained with the Hubble Space Telescope. Okay? And in all these cases, the solid lines are theoretical curves that are trying to match the data. And here is a thermal phase curve of another hot Jupiter. This is the, I was showing you the secondary eclipse. This is going between the primary eclipse, which is here. You don't even see the full eclipse. Look at the scale on the y-axis here. Okay? So the primary eclipse is here, and this is the secondary eclipse. Okay? A few tenths of parts per million again. And this is the thermal phase curve. As the planet's day side is coming into view, the flux is increasing. Okay? So it's kind of cool. So I thought this is, again, an old plot, but this gives you a sense of scale on how advanced we were more than a decade ago. This was with the Hubble Space Telescope. We were already, let's see if this movie plays, we were already able to, we as in the field, were able to make phase resolved spectra of a hot Jupiter as it went around its star. Okay. So that's a thermal emission spectrum reconstructed from spectroscopic observations that I showed you earlier, and same with this temperature profile, also reconstructed from the data. But now you can see these brightness maps as the planet is going around. So to sum up all of this, in the JWST era, in the pre-JWST era, that was with HST, up until a few years ago, 5 years ago, we were able to get these sorts of spectra, in this case, transit spectra, transmission spectra. These are emission spectra, thermal emission at secondary eclipse for dozens of planets. Okay. But the limitation was that in all those cases, the spectra went up to a maximum of about 1.7 micron. Okay. But the proof of concept was there that we could detect all the spectral features in a number of hot Jupiters. There were two, to summarize all of this, there were two limitations. One is the spectral range itself. That, we didn't have instruments that went beyond that. Another limitation was the sensitivity. Hubble is a 2.5 meter mirror. That means we could do these sorts of observations for giant planets, hot Jupiters and so on, Smaller planets was still very difficult. There were a couple of smaller planets for which transmission spectra were obtained, but not a whole lot. And in the last 5 years, the advent of JWST has revolutionized this entirely. So this scene is changing completely now. So what does JWST bring to the table? It brings a much larger mirror. Now we are talking about a 6.5 meter mirror, which is the largest space telescope ever sent, and especially in the infrared. So the second constraint that we had with previous facilities, now we can go all the way until 20 microns and even beyond. With good signal to noise, you can go up to 10 micron pretty easily in transmission spectroscopy and emission as well. So this was the first spectrum of a hot Jupiter that was announced formally by JWST. And you can already see, this is just with one instrument, with one transit, you could see multiple peaks. There is nothing fundamentally spectacular about the science that can come from this, because all we are seeing is multiple water features. We already saw water features with HST, so that's not a big deal. But it was a proof of concept that you can, in principle, extend beyond this. So we were restricted till here. Now, with one instrument, you could go further. But then more results started coming. So there is a lot more people have started doing. So now you can see with one instrument, in this case, they could go from 1 to 5 micron, right? And this is with another instrument, they could go between 3 to 5 micron, but at higher resolution and so on. So this sort of, the coming of JWST has made a huge advancement in both directions we were talking about earlier. One is that it's expanded this wavelength range entirely, right? What does that buy you? Not only that, you could see now multiple features of water vapor. Earlier, we were stuck with just 1 or 2 features, but now you can see multiple features across that wavelength range. And this can keep going, by the way. There is another instrument called MIRI, which can go further. But now it has opened up your molecular space to several new molecules. So for example, this was literally the first, this is the early release science data. And with that first one transit, we could already, as a field, see this huge feature due to carbon dioxide for the first time ever. Imagine this. Until then, CO2 had never been observed in a hot Jupiter. But you see this huge peak. And there are other peaks here, and subsequent studies have argued for the presence of other sulfur-bearing molecules and so on and so forth. But the principle is that now you have enhanced wavelength range, but also the sensitivity, increased sensitivity to see like these very high signal to noise molecular features with higher resolution than we were able to do before. Okay? So that's JWST. I'll come back to JWST quite a lot in later part of this afternoon, but let me cover a few other regions, which is for directly imaged planets. I was talking about transiting planets, but you could also do the same for directly imaged planets. So this is one example of the HR 8799 system. Already from ground, people have been getting this quality spectra. You can see this is remarkable, right? So these are thermal emission spectra of giant planets. So this is for Beta Pic. This is for one of the HR 8799 planets. And these are actual observations. All the black curves are actual observations, which is crazy, right? From ground. But that is possible. This is a picture of the VLT, which was used to get this observation. This is the gravity instrument. Here, you mean?
Yeah, the spread in points is too little.
Yeah, so it's tricky, right? Because K-band, you also have telluric contamination. You have
so
to
they're
correct.
not independent.
No. Yeah. So there is a lot of telluric you have to deal with. I mean, the irony of doing things from ground is that the molecules you're trying to look in the other planet's atmosphere are also in our atmosphere. So you are constantly battling against those, right? So this is why space is so great. So I'll show you what space-based direct imaging spectra look like. That's that. These are spectra obtained with JWST. Okay. Look at the spectral quality. All of this is data. Isn't that amazing? We're able to do these things now. Okay. And these are all with direct imaging. You just get thermal emission spectra. You could get reflection spectra also. If you look in the optical, we don't have that good sensitivity for that right now. But in the thermal emission, in the infrared, you get a lot of these thermal emission spectra with very high quality. Okay, so I've showed you transit spectra. I've showed you directly imaged spectra. And now let's look at another technique, which is the radial velocity technique. So you have so far heard about using radial velocity to detect planets, right? To detect the wobble of the star, and from that constrain the planet properties. But what you can also do is, if you have a high enough signal to noise, take a high resolution spectrum of the planet itself and watch it going around the star, around the center of mass of the system, which means the spectrum itself will be, the planet spectrum is also Doppler shifted, right? So if you have a high enough sensitivity, you can actually constrain the motion of the planet itself. Okay? So that, in that sense, when you do that, so because you already know the expected peak velocity of the planet and the VSIS of the system, this is the systemic velocity of the whole system, you will monitor a certain molecule, let's say carbon monoxide lines. Okay, and then if you detect it, if you detect that molecule, you already know that the Kp and VSIS for that particular planet. Okay, so I'll explain this a little bit more. This cartoon gives the synopsis, which is you have this planet going around the star, right? So previously, we said when we were doing transit, we were just observing at this geometry or here. But now you monitor, you take a high resolution spectrum and monitor as this planet is going around the star. And this is a version of that, which is, this is the time axis or orbital phase, and this is the wavelength axis. And the dark regions here, or the light regions here, are the spectral features of the planet being Doppler shifted in phase. Is that clear? The dark lines, which are stationary, can be due to telluric lines, because we are doing this from ground. So the telluric lines don't change, right? So they stay stationary. And the stellar lines also are quasi-static. In other words, the stellar velocity is a lot lower than the planetary velocity. So the lines of the planets are Doppler shifted much more than the stellar or Earth atmospheric telluric lines. Now you have that sort of a data set. You take a model, a high resolution model of your planet, and cross correlate with that data. And then you scan that space, the Kp velocity semi-amplitude of the planet or the VSIS. You scan all those parameters, all those values in those two parameters, and then you'll see a point in that space where you'll see peak cross correlation. And that you can verify because you already know the Kp and VSIS from the system parameters discovered independently. When you see that peak, you have discovered that particular molecule that you have cross-correlated the spectrum with. I know this tends to be a bit more complicated than the other techniques, so please let me know if anyone has any questions on this.
On the planet surface is different at different points, then this profile can be.
Yes, yeah. So this is talking about thermal emission, not reflection at this point. We're just talking about thermal emission from the planet. But even that, there could be winds in the planet, for example, that will give you another additional component. People have looked at that as well. But this is purely from the planet going around the star. So you have a bulk velocity component, and that's what you're seeing here. Okay. Yeah, so this is a cartoon, but I'll show you some real data as well in a moment. So this is what I'm talking about between low res and high res. So this is low resolution. JWST, the maximum resolution you can go to is about 3,000 in one instrument, but most of the time you bin the data to several hundred. When we are talking about high resolution, we are saying tens of thousands to 100,000. Okay. Not necessarily, you can take multiple species. I'll show you an example of that also in a moment. So these are model spectra we are talking about. So this is the kind of model spectrum that you throw into your data. to cross correlate. So this is showing you an example. These are all of these are different wavelengths. So this this set is at one wavelength range and so on and so forth. So let's focus on any one set. Let's focus on this top set. So you see that this is how your raw data appears at the top. These are frame numbers or time, okay, in this y-axis. That's raw data. You can mask some part of the data when you have a lot of telluric or stellar features, and then you detrend it, which is you remove the stellar and telluric components. There are algorithms that do that, and then you're left with these residuals. Okay, these regions are masked regions because there is just too much telluric that you don't worry about it. And then you're left with these residuals after removing those static components of the star and telluric. And then at the bottom is when you cross-correlate those residuals with a model spectrum. And then you pick up these tracks that are peaks in cross-correlation as a function of your frame number, okay, in time. So that's it. So that you can do at all these wavelengths, different bands, and then you get your peak.
It's a match filter.
Basically. So this is one of the latest examples with the best instrument that's currently available on ground, which is called CRIRIS Plus on VLT. This is an infrared spectrograph. And this is the model that's been cross-correlated with the data. And you can see that in CO, we can get a detection that is 12 sigma detection of carbon monoxide, 5 sigma detection of water vapor. And to answer your question, you combine both of those and get an almost 13 sigma detection of the joint model. Right? The more you put in, you boost the signal even more. Right? So that's what's happening here. Another subtle thing you may or may not have noticed here is that this is a thermal emission spectrum, but you don't see any absorption features. All the features are pointing upwards. Right? And why is that happening? These are all emission features that are coming from the fact that the temperature structure has an inversion in it. Okay? So this was the first example where these molecules were detected simultaneously in a planet with a thermal inversion in it. So for this technique to work, you need to have a good grasp on your theory first, because this technique works when you can have a good guess about what you're expecting to see, and that is the model you cross-correlate with the data and discover. So now you begin to get a sense of how in this field, in exoplanetary atmospheres, you always have to go hand in hand between theory and observation, because your observation planning, as well as in this case, inferences, are informed heavily by the theory at hand. Okay? So this was the first detection of a thermal inversion and these molecules from ground together, all of that together. Telluric, right? So there is a lot of telluric H2O. So you want to be able to correct it very accurately, and there are still residuals. Yes, CO, you don't have that much CO on the Earth's atmosphere. Right?
Your point that because of the inversion, the kinetic temperature of these molecules is more than the surface temperature of the star.
No,
You see it in emission.
So it's a little bit more subtle than that, which is and very interesting point actually. Maybe I should go into this.
Why don't you see it in absorption?
Exactly. So when you have a temperature profile, this is your Kirchhoff's law, right? So if you have a temperature structure that goes like that, right? So let's start by saying if I have an isothermal atmosphere where the temperature profile goes just like that, what do you expect for a spectrum? Just a Planck function, right? So you'll expect a Planck function that goes like that, something like that, right? Okay. Now I'm telling you that my atmosphere has a temperature gradient that goes like that. So what would the spectrum look like? Right. So, but you have a whole spectrum, right? So you'll have various molecules absorbing at different points. So what you expect is, a spectrum that goes like that, right? Absorption features due to various molecules. Now, if I tell you that my temperature structure is going like that, the same features will be inverted, right? Why? Because now you have a hotter surface on top of a cooler emitting region, which is your Planck function of the continuum. So the same features can turn around and become like that. That's what's going on there.
So this is not taken against the star.
No. This is thermal emission from the planet itself, right? So that's a model calculated at high resolution from that temperature structure. So you'll.
When you observe.
Oh, so that's another important point. So in thermal emission at secondary eclipse, you have, this is the configuration, right? The planet is going behind the star. So here you see F star plus F planet, right? But what you do to get the eclipse depth is you wait until the planet goes behind, and then you have your F star alone. Exactly. Then you can get a delta lambda, in this case, of Fp or F star. So there is you're no longer seeing the illumination itself. You divide by that, right? So then I can go for hours on this particular topic. Okay, so good. So if you do that, the planet star flux ratio, then this same spectrum goes like this basically, right? Because in the Rayleigh-Jeans tail, your Planck function asymptotes to a t over lambda to the fourth term, and in this ratio, the lambda to the fourth cancels out, and if you're left with just t planet or t star, and that's why this asymptotes to a constant, which is an interesting property of this function. Okay. Anyway, so we are still in the lower lambda level regime. We don't go till the Rayleigh-Jeans tail just yet, but that's what you can see. Okay, cool. So that was obtained also with the VLT.
Fiducially are drawn the y.
Sure, yeah. I mean, it is supposed to be at the center.
Like if I CO seems at the center,
Yeah.
while the water seems.
Yeah, I mean, within the error bars, it's all within error bars, but you do expect, as someone earlier asked, what happens if you have winds in the planet? So we are not considering all of that just here, or if there are inhomogeneities in the emission. Could be, right? So, but here the error bars, I mean, the true values are within the error bars, so we don't particularly bother about that. But in principle, if your chemistry is inhomogeneous on your surface, you can expect the velocity, the exact centroids to be different between different molecules. So yeah, so here you can scan for different abundances also. You don't have to restrict yourself to one abundance. In this particular case, it doesn't matter. You get, this planet is hot enough that is close to equilibrium. So it's fine. Sure. Yeah, you can call it an SNR basically. I mean, we literally call it signal to S over N here. Yeah, so it is an SNR. I just colloquially you call it a sigma, but it's actually a signal to noise. So basically taking the peak of the cross correlation and the noise is from the surrounding region. You take an average noise and then you divide them to see how big your peak is. Yeah, so that's the trick in cross correlation in this technique is that you can't, by looking at the observation, you can't pick out the molecule. Because the observation is done, that's your observation, not for that particular planet, but for another planet. That top row you're seeing is the data. So this is plotting, in simple terms, flux as a function of wavelength and time, or frame number. Each frame number is observed at a different time or phase. Okay, this is just a contour of the flux. So each row, there are 40 rows or so here, and each row is just flux as a function of wavelength. Okay, so you have a 2D image basically in time and wavelength, and that's what you, after you clean it up, after you remove the quasi-static components from the star and the planet, you are left with these residuals. And then you cross-correlate those residuals with your model spectrum. And then wherever your CCF, the cross-correlation function, peaks, is where you detect that species or that model that you're injecting. Okay? Please, please.
So in the model, I'm assuming the line ratios depend on the kinetic temperature of the molecule.
Yeah, so I think like when you're talking about kinetic temperatures, usually you're referring to non-LTE type effects.
Yeah.
Here, all of this is in rough thermal equilibrium. It's an LTE atmosphere.
But still, you have a forest of lines.
Yes, yes.
And the relative strength of the lines probably depend
On
the
the
local population.
equilibrium temperature, yeah.
Equilibrium temperature.
That's right.
You're doing a cross correlation. So in the cross correlation, you could, in principle, try different models at different temperatures.
Yes.
And that gives you a direct measurement of the temperature.
Yes, people do, and I'm going to show you.
Okay.
Next, when we, so I've just finished the observations part. I'll do that in the next minute. And then we'll talk about retrievals, and I'll show you a retrieval with high resolution as well, where you can derive the temperature structure. Okay, so those are all the techniques that we have talked about. Just to summarize, we've talked about transit spectroscopy, we've talked about direct imaging, we've talked about radial velocity, how you can use radial velocity to detect species as well. And we'll talk a lot about the background, some of the theory, how chemistry changes as a function of height, and how you would infer these observations. What is happening at the forefront of this field right now is, so far I've only showed you hot Jupiters, giant planets, hot planets. The promise in this decade is that now we have the James Webb Space Telescope, we have the extremely large ELT telescope that's coming towards the end of this decade. And in addition to just having a higher sensitivity and longer wavelength range for giant planets, for hot Jupiters, we are now entering a regime where we can also study small planets. And by small, I mean this sub-Neptune regime that I talked about at the very early part of my talk, planets between Earth and Neptune. We are now able to probe even those planets with JWST. Okay? So that is where the future is. And for the first time, we are also demonstrating that we are actually sensitive to biosignatures, molecules that could be potentially indicative of life. So we'll also talk about that in what is to come. Okay? So it's a very exciting time in that sense, is that we have gone in just 5 years from looking at just mostly hot Jupiter, hot giant planets with the Hubble Space Telescope and a few ground-based facilities, to now saying we can go all the way down to habitable zone planets and discover molecules, and even molecules that could be indicative of life elsewhere. So I'll stop here for this part. Next. We can take questions. I can dive into retrieval if you want, or we can take a break.
Yes, there's a tea break. So 5-10 minutes, we'll take more questions, and then we can have a tea break and then move on to next.
Yeah. Any more questions? Yeah, go on.
Okay, so first, yeah, you go ahead. Yeah, you.
Yes, so that was done for a direct image planet, beta pic I showed you. It was done for that, where someone could actually measure, they measured the spin of the planet, but there are also studies which argue that they can measure the wind speeds if you use molecules. Yes. So you could also look at these things in transit. So I only showed you in thermal emission spectra, but you could also look at them while they're transiting. And then Doppler shifts can give you a constraint on the wind speeds at the terminators, for example. Okay. Direct imaging, whichever side, you don't know which side, you're just getting a spectrum of the planet. It could be, if it is, depends on the orbital configuration of the system, right? So you have, if your star is here, let's say, and I'm the observer, then yes, you're right that you have half of it day side and half of it night side. But the star could in principle be anywhere. Right, you're nulling out the star and you don't know the exact orbital geometry. All you know is that you're detecting light from a planet. You're seeing a blob, you know that there is light. Beyond that, you don't know the exact demarcation of the day versus night. Yeah, please, yeah. You can. The problem is that the signal to noise will be very low, right? You have R of 100,000. So the error bars on each individual point is huge. So you can't actually see anything. Right? So the only way to pick out, for each individual point, your error bar is large. But when you do cross correlation, you are summing up the contribution from thousands of lines. And collectively, they give you a reasonable significance. That's why you sum them up.
Any questions? Of course, there is. Oh, yeah.
Yeah, please, yeah.
Yeah. At the same time, others are helping. So, how do we know that whether the atmosphere features of the air because it is impacted by the opportunity?
Right. Yeah. So very good question. So the question is, if you have one planet transiting, you have a two-planet system, and one is transiting while another is occulting. How do you know? How do you differentiate between those? So this is supposed to be a hypothetical question, but we actually see it in real time. We can model these things because your transit is giving you the absorption, whereas the occultation is giving you the emission. So for example, you would, if you're looking what is known as the white light curve, which is you bin all the wavelengths together. If you have a pure transit, you would see a transit light curve like that. But if you have an occultation, then your baseline can be different, right? So you could see, for example, I don't know, it'll depend on the situation, but you could see a bump in middle of your transit because of another planet interfering with your transit light curve. It could be that, or it could be like this, and that's also degenerate with star spots. You can also have star spots which can act as an occulting body as well. You could have a spot that is hotter than the average photosphere or cooler than the photosphere. So all these sorts of contaminations we have to deal with on a regular basis when we look at these planets with JWST. And then you can model that. Yeah. So you can model it. Her point was that if you see both events happening at the same time, how do you separate them? And the way we do that is that if we know the orbital parameters of the other planet, you can exactly model its contribution. If you know its radius, even better. and then you could use its temperature. In this particular case, if it's an occultation, you could use its brightness temperature as a free parameter and fit for it as well. Okay? So we do this regularly, where we can have multiple planets occulting, and you model both at the same time and try to retrieve both the properties simultaneously. Okay, but good question. Thanks.
Students first.
No, there is no hand. There is no hand.
Thinking of this, the emission profile which you explained, I can see that if you have at the upper layers temperature monotonically increasing, you get those features in emission. But in the retrieve feature you showed, the temperature doesn't to some value and it stays constant. So the temperature increases but then stays constant.
Oh yeah.
In the constant part, if the optical depth is unity, then there's nothing. There's no signal.
But that never happens.
So we just got lucky. That's not.
Yeah, no, that never happens. The reason for that is that your pressure is decreasing upward, right? So your photosphere, your infrared photosphere is usually somewhere here, right? So that is between about 10 to the minus 5 to 0.1 bar or so.
That got lucky that nature gave us the right oscillators.
Sure, but like even just like if you just take hydrostatic equilibrium for a planetary atmosphere, you will see that your optical depth for most molecules will, the densities will fall way lower than tau of unity by the time you get to 10 to the minus 5 in the infrared. So of course, if you talk about UV, that's a whole different.
Yeah, then everything is
everything is different. But in the infrared, by that time your density, number density already goes very small. So it doesn't matter what the temperature profile is at that point. So if you look at the errors on these temperature profiles, that you will see that they will be very well constrained in this part of the atmosphere, and then they will diverge like that, right? And same at the bottom. So because you have information only in this part of the spectrum of the temperature structure.
Okay, then we'll reconvene at 4 o'clock and we'll begin the next part, Madhu's next talk.
Thank you very much.